Okay, so now we start our session 3 for this class. Okay, so using the sufficiency to find the MVU estimator. So assuming that we have been able to find a sufficient statistic of x for theta, then we can use that theorem to find the MVU estimator. Okay, so first let's take a look at this example, then we will go to the theorem. So we'll continue from this example. We already know that A hat equal to simple mean is the minimum variance unbiased estimator. Okay, so then we will use the raw theorem to uh, to create a sufficient statistic. So when an efficient estimator does not exist and the CRLB is no longer viable, the procedure for finding the MVU may be implemented in two different ways. They are both based on the sufficient statistic. Okay, so for any unbiased estimator of A, let's say A equal to x0 and determine A hat equal to expect A conditional T, then the expectation is taken with respect to this. Or the other way is to find some function g so that A hat is g of T is an unbiased estimator. So for the first approach, we will let the unbiased estimator to be this and then determine this. To do so, we will need some properties for the conditional Gaussian PDF. Okay, so for a Gaussian random vector with mean vector this and covariance matches this. This is typical, right? It's a typical formulation for Gaussian random vector. You need a mean for each variable, and you need variance and also covariance. Okay, so then there will be expect x condition and y. In fact, this and this is a identity. It's a probability identity. But if it's not clear, then there will be an appendix to prove it. Then applying this, we let this and y equal to that and note that xy is equal to x0 and summation this, which is equal to this multiplied by this is what? The original complete set of data, right? It's an original set of data. And primitive, it's primitive. It has not been processed in any way. So you have x0 equal to this multiplied by that, and y equal to this multiplied by that. Hence, the PDF is n mu c, since this represents a linear transformation of a Gaussian vector. Okay, so where mu is equal to L, this C equal to this, and we have finally from this we get notice that we have this equal to A is equal to expect of this equal to this multiplied by this, then we get this. So what that means is we are using this procedure. We we first we take an unbiased estimator. Of course, if you take the first sample and take the expectation, it's definitely unbiased. So this thing is easy, right? This business is easy. But to determine this, it's a bit more difficult. But if you determine this and then you take the expectation that you get the MVU, that's what we are saying here. So we want to do this and then take the expectation of that. You need this. But before you get that, you need this, right? You need mu and c and x and y. You calculate x and y and mu and c, then you use this and this to obtain respect of x condition on y, and then eventually you get a hat equal to this. That is the MVU. But this approach requiring evaluation of a conditional expectation. Then of course we are using this DC level as an example, but it's usually difficult if you have other format of the signal model. But and then turning our attention to the second approach, we need to find some function of the data so that when A is equal to G, it's unbiased and it's minimum variance. Okay, so we need a G to be unbiased. Then it's a little bit of empirical. By inspection, this G is equal to X divided by N. Then it yields this. That is the MVU. Okay, it's the MVU. All right. So there is this theorem, Rao, Bagwell, Lehman, Schaeffer theorem. And if beta hat is an unbiased estimator and T is a sufficient statistic, then theta equal to expect this is a valid estimator, unbiased, and then it's of lesser or equal variance than that of theta for all theta. If the sufficient statistic complete, then this is MVU. Okay, so what that means is if you take a theta, then it's better, right? It's lesser or equal variance, so you are taking this theta hat to be better than this theta. Then you do again and again, you're getting better and better. You get a better and better estimator, and it's unbiased. So let's take a look. You have a theta, and you are doing this RPLS process. So as a result, you are getting better and better, and eventually you get to MVU. But of course, it's not guaranteed. It's not guaranteed. It's just like an optimization process to get you to proceed to get better and better, but it's not guaranteed you get MVU. Why? Because if you take a look, you might fall into here. You get better and better, and eventually get to here, and you never go out. You never go out. This is not like any optimization problem. If you try to optimize and then your objective, you have a procedure to get you better and better in terms of a better objective value. You just get better and better, but it's not guaranteed that you get the optimal point, because some of the region are complicated. You fall into the so-called local minimum or local optimum. You don't get to the global optimum. It is possible, but anyway, it's a difficult problem by itself. So it doesn't seem like we have a lot of options. It's not like that, right? So this is like, if we don't have other options, this is a procedure we try to move on. Okay, So now we will skip a few sessions and go directly to page 116, 116, 116. So yeah, let me see. Okay, so let's start from here. Okay, so now let's go to session 5.6. We are doing extension to a vector parameter. And as we expect, we do scalar first, then the next thing is we go on to a vector version. So vector statistic P of x equal to T1, T2, all the way Tr is said to be sufficient for the estimation of theta if the PDF of the data condition on the statistical P of x, T of x, theta does not depend on theta. This is to say that P of x condition on T theta is equal to P of x condition on T of x. Let's watch carefully if P of x depending on T and theta is equal to P of x depending on T of x. What that means is theta is no longer necessary, right? If theta is no longer necessary, then T of x has sufficient information, right? It provides all the information needed to describe x. 我用中文再讲一次哦。如果 P of x depend condition on t 跟 theta 等于 P of x condition on t 的话，那 theta 就是什么？就是不必要的，是多余的。换句话说呢，这个 theta 它的 information 其实完全存在于 T of x 里面，所以 T of x 就完全具有充分的资讯了，对吧？对不对？这样子的说法是不是更能符合这个所谓 sufficiency 的这个概念 ？T of x 它拥有了充分的资讯，所以我们不需要 theta， 我们也能够描述 P of x， 就是这个意思。哦，这就仿佛说，你有很多资讯，但是有一些是多余的，那多余的其实是可以去掉的。当你把多余的资讯去掉，剩下的也是 sufficient 了，对吧？剩下的东西就是 sufficient 了。哦，就是这个意思。Okay, so if P of x exists so that we are interested in the minimum sufficient statistic or the T of minimum dimension, and then we go to the vector version of the Fisher factorization theorem. If we can factor the PDF P of x theta as this, where g is a function depending on only T of x and theta. I'd like to highlight this sentence, depending on x through T of x. It does not depend on the data of x individually. 也就是说，在这个 G of x 里面不能够有 data x 单独的一些项单独的数值存在 G 里面，不能有 data 的数值在 G 里面只能存在 T， 它只能透过 T 去影响 G， 这样子 T 才是 sufficient。好，如果 x 个别的值是会有影响到 G 的话，那这就不是 sufficient 的。这代表个别的值其实是有意义的嘛， 对吧？它有额外的资讯存在嘛，所以 T of X 就不是 sufficient。那如果它所有的资讯都是透过 T 去影响到 G 的话，那换句话说 T 就是 sufficient 了。Okay, so then only through T of X, and H is a function depending only on X, and T of X is a sufficient statistic for theta. Conversely, if T of X is a sufficient statistic for theta, then the PDF can be factored into that form. Okay, so this is like a two-way implication, which we say sufficient and necessary. 充分必要条件。好，就是说，如果这个式子成立，那 T of X 就是 sufficient statistic。如果 T of X 是 sufficient statistic，那就会存在这个式子，会存在。只是说，当然怎么找到它，这个有时候要用一点技巧。那更多的时候其实是经验跟巧合啊。就像我们先前做的几个例子，其实是透过一些方程式的调整跟重组来达到这个目的的，所以这件事情并不 trivial，并不是很系统化的可以达到，在很多 signal model 里面并不会很系统化的。好，那我们就来看 example 5.9. We have a sinusoidal parameter estimation. Assume that a sinusoidal signal is embedded in WGN. This is a typical problem. We did it many times. The amplitude, frequency, noise variance are not unknown. Okay, so now we have a new version. We have a new version of the problem, right? You have a lot of things unknown instead of just one single scalar. You have multiple, which is A, F0, and sigma square. The unknown parameter vector is therefore theta equal to A, F0, sigma square transpose. The reason we check transpose is that we are used to a vector form. We are used to a vector, like this is a column vector, right? A column vector. We are used to a column vector. So we have to take a transpose to make a column vector. And then the PDF is P of X theta equal to 1 over 2 pi sigma square n divided by 2 exponent of this thing. This is Gaussian, right? This is Gaussian. Then expanding the exponent, we have this second order polynomial expansion. 这是二阶多项式展开嘛？二阶多项式展开。Okay, so you get this. Except there is an extra summation in front, but it doesn't matter. Inside of it, it's a second order polynomial. Okay, so you get that. Now, because of the term where F0 is unknown, we cannot reduce to have the form expressed in 5.11. 5.11 is like this: theta and T of X. Like what I said before, we cannot have unknown parameter to mix with the data. 就是说这个 theta 不能够跟个别 x 的值混在一起，但是这里已经混在一起了，有没有发现 f0 跟 x 混在一起了？ So we cannot reduce this to the form. So on the other hand, the frequency were unknown, the unknown parameter vector. I'm sorry. 更正一下。If the frequency is known, the unknown parameter will be this. The PDF could be expressed in this form. Then we continue on here. T of x is a sufficient statistic for A and sigma square, but only if f0 is known. Okay, so in other words, if f0 is known, notice that the frequency is known. Notice this sentence. If the frequency is known, the unknown parameter will only be A and sigma square. F0 is not unknown. Okay, F0 is a constant. Then the PDF is placed in this way. It doesn't matter x0 in a mixture with f0， 就是说这个 theta 跟 f0 混在一起的状况就没有关系了。为什么？因为 f0 是 constant， 它不是一个 unknown parameter， 所以在这种情况之下，这一项就没关系，因为 f0 我们就把它当一个 constant 就好了。这时候，这个项又可以写成 g of t of x theta 了，对吧？对不对？因为 sigma square 跟 a 并没有跟 x 混在一起，并没有跟 x 混在一起。Okay, so now we will be able to write t of x as this and this. Then t of x is a sufficient statistic. Then, of course, it depends on what's known and what's unknown, right? It depends on what's known and what's unknown. So as you can see here, a sufficient statistic is really a thing, a non-trivial business. It's not like very trivial. It's not like that. Okay, even in this sinusoidal signal model, we consider this problem to be a very simple problem in engineering. We have a lot of problems more complicated than this. So as you can imagine, it's going to be very complicated if you try to find a sufficient statistic for complicated signal model. Okay, so now let's go to the next example. Example 5.10, DC level in Y noise with unknown noise power. So if we have a xn equal to A plus W, where Wn is Wgn with variance sigma square, and the unknown parameters are A and sigma square. Recall, this is not sinusoidal. This is DC level, and sigma square unknown. So we can use the results of the previous example to find a sufficient statistic of dimension 2 because we have 2 unknown. So that the unknown parameter to be A and sigma square, and that f0 equal to 0 in the previous example. This is a little bit strange, but let's get used to it. If you set f0 equal to 0, then what happens? What happens is you have cosine 0, right? Cosine 0 is equal to 1. So as a result, you have x equal to A plus W. So if f0 is 0, then this sinusoidal problem degenerates to a DC level problem. Okay, that's what we are saying here. So you can let f0 equal to 0. Then we have our sufficient statistics, this one. Because of what? Why are we not doing any calculation and then we get the outcome? Why is it looking so easy? It's not easy. We go from here to here. Okay, let's 稍微慢一点，让大家看一下这个对应关系。就是如果你把 f0 设成0的话，这个 f0 就0，所以这个 summation x cosine 就变成 summation xn 乘以1，对吧？对不对 ？cosine 0是1嘛，所以就 summation x， 然后 summation x square， 所以这整个东西就变成这整个东西。所以 如果让 f0 等于0的话，这里的 sufficient statistic 就会变形，变成很简单，就变成这个 sufficient statistic. Okay, so I think that that is a very good example. Corresponds. The two examples correspond with respect to each other. Okay, so another observation is that if we know sigma squared, this summation is the sufficient statistic for A. If A is known, summation x squared is a sufficient statistic for sigma squared. So in this example, the same statistics are jointly sufficient. But this will not always be true. This is a coincidence. Since we have two parameters to be estimated, we have found two sufficient statistics. We should be able to find the NVU. Okay. So the process will be the same, will be similar to scalar version. You do this and then you take the expectation. Okay. Except it is a vector version. It's a vector version. Okay. So let's take a look at this DC label problem. DC label in WGN with unknown noise power. We first need to find the mean of the sufficient statistic. This is to say that if we know the sufficient statistic, then how will we find a good estimator? Okay. If this is not clear, I would recommend you to check back to, let me see. I would recommend you to check back to page 109. Page 109, theorem 5.2. OK， 就是可以稍微 review 一下109页讲的那个 theorem 5.2. OK, it's the same thing. OK, it's the same thing except this is a vector version. OK, so let's take a look at this DC label in WGN with unknown noise power. So we have sufficient statistic, assuming that we have it. Okay, assuming that we have it. And then take the expected value. You expect this, you get that. I think this is trivial. Okay, this is trivial. So expect of this, you get NA. Expect of this, you get N sigma squared plus A squared. Then you get, clearly we cannot remove the bias of the first component of Px by dividing the statistic by N. Okay, but this will not help the second component. It will be obviously that T2 estimate the second moment and not the variance. Okay. If it's not clear about what is the moment and variance, I cannot really 没有办法很讲细节，因为这个是几率那一门课在讲的哈。Second moment， 在 mu 等于0的时候 ，second moment 就是 variance， 但是 mu 不等于0的时候 ，second moment 不是 variance。Okay, so the transform will be, we do some transformation g t of x. You divide this, and then you get this, Okay. Then expect of x bar equal to a, and expect of the second term equal to this. But we know that x bar is equal to that, so that expect of x bar squared is equal to this. And then we have expect of this equal to that. So if we multiply this by this, then it will then be unbiased for sigma squared. So the appropriate transformation will be you divide the first one by this, and then divide the second one by this. since T1 is sufficient, it's part of the sufficient statistic, so we can use it as the second part, right? We can use it as the second part without trouble because T1 is part of the sufficient statistic. OK， 就是说这个 T1 它已经是 sufficient statistic 的一部分了，所以我们把它用在第二个部分是没有问题的哦。你不能够拿其他的参数把它放到第二个 component，这样是不行的，因为它不是 sufficient statistic。但是既然 T1 已经是了，所以我们把它放在第二个做一个调整是合理的。OK，so you do this transformation, you get that。大家知道为什么？这里可能有点复杂，就是说大家稍微慢一点想一下哈，为什么这里 transformation 要做成这个样子？因为刚才我们已经算过了，如果你去除以 n 的话，它 expectation 会变成这样。这个是什么？这个是 bias 的。这个东西理论上应该要等于 sigma square 才是 unbiased， 可是我们算到最后的结果是它竟然是这样。如果它是这样，那就是 bias。那 bias 就没办法了，我们就没办法说它是 unbiased estimate 啊。所以这时候有问题了。所以我们怎么调整它呢？是用这个方式做调整。这个方式在调整过后，这个不好意思，这个方式，我们用这个方式做调整。如果调整完之后，那你再算一次，它就是 unbiased 的。OK，so it will be written this way. So if we have this as the like the G, then our theta will be this. For the first term, we have no problem, but we have a little bit trouble with the second term. Okay, we have a little bit of trouble for the second term. So this is the NVU for this. The normalization factor of this is due to the 1 degree of freedom lost in estimating the mean. Okay, so I think that will be the end of this session, and basically we generalize the scalar version into the vector version, and then we do an example for DC level. And notice that this DC level problem has two parameters. It's no longer a single parameter. It's a two-parameter problem. Okay, so I would recommend you to read the details, and some of the derivations you may want to try to practice, try to derive it. Part of it has been done in, I guess, undergrad probability class. So I recommend you to do a little bit of review and practice. Okay, then we'll move on to the fourth session.